How do we go live up here? Going live. You ready?
Yeah.
Oh, we're a little behind here.
I think it's gonna knock.
We're a little behind. All right, everyone. Welcome to the W2CXM / Alpha CubeSat balloon launch live stream. We had a few technical difficulties going into this, but now we're actually picking up kind of intermittent video from everyone, and are ready to get this show on.
Yes. And we have launched.
Yeah,
So we're going to pull up some video for you guys about the balloon and its positioning on a Google Earth map.
Yes.
And we're trying to get some live feed, and we'll show that to you guys as
momentarily
soon as possible.
Yeah.
But right now, you can see
We've got
this is our estimated flight path for today.
including altitude information. Okay.
And as of now, it's right on the beginning of its path. It's not following it exactly.
Right.
Um,
We're about here.
yeah.
Okay. We can get altimetry for you as well. So we're at approximately 5,000 feet and climbing at around 25 miles an hour. Awesome.
And today it was expected to rain a little bit, so we actually delayed our launch from an earlier time that was supposed to happen at noon or so today, but now we're launching at around 3:30, and so we're really excited to see how the conditions will have changed throughout the day.
Yeah, with the weather in the Finger Lakes region, it's always difficult to predict this, so that hence the all the kind of last minute scheduling. But we're really excited to get going today.
Yeah. There's definitely some light rain.
Yes.
Which is not necessarily the best for a balloon path, and it can create some mission issues. So we're hoping that nothing goes wrong with that. We've gotten the okay from our experienced balloon launcher, Mike. And what is Michael's last name?
Everyone calls him Mike Hojo. He's
Mike
got
Hojo.
a very difficult last name to pronounce. We can if you're really interested, go look at the W2CXM page. He runs the amateur radio club at Cornell. Eleanor, do you want to give everyone an outline of the mission today?
Yeah, I'd love to. Okay, so this balloon launch is including two different missions. One is the payload that that Mike is putting onto the balloon, and we'll watch some snippets from him about that later. The other is the Alpha CubeSat mock-up. So our Alpha Cube satellite that both Ben and I are working on and will launch later this year is a cube satellite that deploys a solar sail, and
a free-flying solar sail.
In space, it will be free-flying. Mm-hmm. For today, we have a mock-up, so it's actually tethered on a pretty long tether. Mm-hmm. And we'll get to see some video of that deploy, and we'll get to see how it escapes from the spacecraft and where it goes after, and kind of get an idea of what will actually happen on launch day in space. So that's what we're excited to see visually today. We'll also get a lot of data about how our system works. So we are going to have a pretty long run today. It'll take an hour to get up and an hour to go down. In the actual launch, it will be... Oh, here we go. Let's see. Okay, so our Alpha CubeSat will have 6 holograms on all the sides, and those will actually be selected by different groups later this year.
Hello, Benjamin. Hello, Benjamin.
And so now we're going to talk to the artist who's
Okay.
adding those holograms.
What do we do?
And we actually...
We're ready to rock and roll.
We're ready whenever you need us.
They're ready to rock and roll.
Yeah, so we're going to talk to a light sail expert and the artist behind our holograms momentarily. We'll get into the whole background of the mission, but basically they're kind of they've been working on this for the last few decades, and it's finally time to turn the science fiction and kind of theoretical stuff that they've been working on into science fact.
Should we start, or will you let us know when you're ready?
Yeah, please let us know when you're ready.
Awesome. So welcome C. Banks and Greg Matloff. Hi. We're ready.
Hi.
Hi.
Welcome to the live stream.
You're ready.
You
are
Okay,
ready.
should I begin?
Yes.
Okay. So I'm going to talk for about 9 or 10 minutes about light sailing, and I'll begin a little bit with its history. It actually is a 4-century-old concept. Johannes Kepler, around the year 1600, noticed that comet tails always point away from the sun. So he realized there was something, he called it a wind, unfortunately, because it's not the solar wind, it's the solar breeze, the photon breeze, photon pressure, pushing the material in the sail directly away from the sun. The next person who got involved in this was James Clerk Maxwell, around the year 1860, who actually was able to put radiation pressure into his theory of photon radiation pressure into his theory of electromagnetism. This was finally codified by Albert Einstein in his glorious year of 1905 in a notable contribution to early quantum mechanics, where he noted that photons, although they're massless, do carry a momentum and can give you a push. In Russia, people like Tsiolkovsky and Zandler, between about 1920 and 1930, began to explore the idea, and others did in other parts of the world, including the US. Finally, before 1980, or maybe around the early 80s, Robert Forward, who was a remarkable guy, a real visionary space scientist, did note that the solar sail, the photon sail, did have applications for interstellar travel. So, of course, what happened is people then had to come up with doing some actual space experiments. The first of these was by I forget if it was still the Soviet Union or the Russian Space Agency. I think it was still the Soviet Union. I believe 1986 or 1988 or 89, I forget the exact dates. A test reflector called Znamya was unfurled from a Progress cargo ship at the Mir space station. And really, they were testing solar sails, but they couldn't admit that. So instead, this was supposed to be a reflector that would ultimately demonstrate that you could reflect sunlight down to Siberia in the winter. So people working on the very profitable oil wells there wouldn't get very depressed, get seasonal depression. And of course, you people in Ithaca probably know a little bit more about seasonal depression than I do in New York, because you get a lot more snow. Anyway, there had to be real tests in space of this, and the first successful one was by the Japanese. In the year 2010, they launched Akados, which is a solar sail which will ply interplanetary space between Earth and the orbit of Earth and the orbit of Venus until who knows when. Last I heard, they were still able to get communications with it, and they did have a scientific payload on board, so they were able to get some information on cosmic gamma ray sources. NASA was able to soon launch the first of its test drag sails, NanoSail D2, which I believe also was in 2010, in low Earth orbit. Light Sail 1 and 2 of the Planetary Society have both worked very nicely in low Earth orbit, and they demonstrated that you could actually use solar photon pressure for orbit raising. Now, my interest in this thing began in around the year 1980, and I spent most of my scientific career looking at various aspects of using the solar photon sail for interstellar sailing. Now, what I've been able to do is demonstrate that if you use a material like graphene, you can get a robot to the nearest star in a few centuries. And that's very nice. So people might say, well, you can probably do it with people too. The problem is if you're launching from the sun, because of the inverse square law, you're going to run out of push pretty quickly. So you need a very large acceleration. To get humans there in a few centuries, they have to be re-engineered to take accelerations 50, 60 gravities or so. A more reasonable acceleration of a couple of gravities could get an arc, a sizable arc behind a solar sail to the nearest star within 1,000 years, if it unfurled within something within 1/10 of an astronomical unit from the sun. Now that's very nice for interstellar migration, but it doesn't really say very much in terms of getting back information quickly. So we have to fast forward to an idea that Bob Forward also pioneered called laser sailing. If you have a laser or a microwave maser, and you can get around the inverse square law and push photons, intense photons, against a sail, even when it's very far from the sun. So, okay. This idea stayed in the background for a number of years until 2015, 2016, when a former Russian oligarch who immigrated to the US and made a bundle named Yuri Milner said, let's do this with a terrestrial laser and a WaferSat, very similar to what you're launching, and push that to Alpha Centauri in maybe a 20-year mission. Now, we don't know. I'm an advisor to Yuri Milner's project, Starshot. None of us will say it's feasible. All of us will say it's very, very, very challenging. But one particular challenge for this thing is keeping the sail in the beam under very high acceleration. And what happens is you might be accelerating at 5,000 or 10,000 Earth gravities, but the beam is moving because it's the lowest point is on a high terrestrial mountain. And of course, it's pointing towards Alpha Centauri, the upper point, the terminus. Now, to keep the sail in the beam, the sail a moving beam, it must have a curvature. It must be spherical or parabolic shape. On the other hand, anything at 5,000 or 10,000 gravities is going to collapse to be a flat sheet in milliseconds. So how do you get around this? And the way you get around this is with an appropriate diffraction pattern of a spherical object on the sail. And of course, one way to put this diffraction pattern on it is holography. And what this is doing, what this little mission, this inexpensive CubeSat will do, is test holography in space. It will demonstrate that a hologram in space, will perform pretty much the way a hologram on the Earth. And what it will do is raise the technological readiness level. So I'm going to pass this over for the next 5 minutes to my wife and collaborator and partner, the artist C. Bangs, who created, under Bob Forward's suggestion, a holographic message plaque for NASA. And basically, her work is what is flying with the holographer Martina Monrovia is what will be flying on the CubeSat Alpha. And of course, maybe even you can see some of it on the mock-up. Here she is.
So we're I did the holograms with Martina a couple of years ago from sculptures that I created, little sculptures, and then I took them over to the Holo Center and we did holograms of the sculptures with reflective material that Mason Peck and his group sent to me to increase the reflectivity. And we're planning an exhibition of the CubeSat with another variation or another version of the CubeSat that will be the same size as Alpha CubeSat, and that will include the CubeSat, the variation of the CubeSat with the holograms on them, and then in addition the sculptures, the panels with retroreflective material, and panels that will include the contributions of the Alpha CubeSat team, that will be both the writing and the visuals that the Alpha CubeSat team has created, as well as monitors that will show the deployment of the sprites out of the CubeSat, and the sail being deployed out of the CubeSat, and will also include a monitor for viewers of the exhibition to include messages that they would wish to put on a holographic message plaque, which could contain a hypothetically unlimited amount of messages. So we're inviting the viewers to participate in this exhibition and include many, many different messages for the Alpha CubeSat holographic message plaque. I think that's pretty much what I have, and we're looking forward to seeing the deployment of the sail from the balloon.
And I guess if you have any questions or you'd like anything clarified of what we just said, please, we'd be happy to address them.
Awesome. Yeah, thanks
Awesome.
for that.
Yeah, thank you for that.
Thank you.
You're welcome. Very good. Thank you for all the work you've been doing on it. It's great. It's also very unusual for me to be part of a flight effort, something that actually is going up in the air and above the air later this year. So it's really wonderful. We've both been having a good time with this.
Yeah, stay tuned to get more interesting.
So we'll
Yes.
So we'll switch over to the link that shows.
Okay,
Thank
you're welcome, and we look forward to meeting you folks in person.
Yes.
Without masks, hopefully, in the not too distant future.
Looking forward to
Okay,
it.
so we'll go over now to watch the. Okay, bye-bye.
Bye-bye.
Bye.
Thank you.
Hi, thank you.
Thanks.
Welcome, thank you.
Awesome. So, welcome back, everybody. As was suggested to me, we actually hadn't introduced ourselves. So, would you like to go first, Eleanor?
Yes, let's do that. Okay, hi, I'm Eleanor. I'm a junior at Cornell studying mechanical and aerospace engineering. And I've been on the Alpha team since last year. Before that, I was actually working with Professor Peck, who is the PI of this, on chip satellites. And so with our mission, we will be deploying 4 chip satellites on the solar sail, which we'll talk about later. Super exciting. Satellites that are only about this big. So other things, I am, let's see, any other prompts, any other introduction?
Any of that? Well, we're gonna be spending a lot of time with you, so I'm sure you'll get to know us a bit better.
Exactly.
Yeah.
So if you have any mechanical engineering questions or questions about these structures that are going on for a CubeSat, the deployment, etc. I'm the person for that. And Ben is part of our publicity team, the head of our publicity team. So
Yeah, so hi everyone, I'm Ben. I'm also a junior at Cornell studying economics and astronomy. I joined Alpha a while ago just to kind of like, write about it because I thought it was really cool. And then look where we are now, doing a crazy live stream of this balloon launch. Yeah, so aside from this, we're also, as C and Greg alluded to in the conversation that we had, doing this like golden record 2.0 really cool publicity initiative coming up, where basically everyone will get the opportunity to vote on which holograms are going to be the first to be sent into space aboard Alpha. So if you recall kind of the golden record that was sent on the Voyager missions in the 1970s out to the stars, we're kind of aiming to do that again, or at least getting people thinking about what would we send. So that's really exciting, and this whole balloon launch, light sail deployment, Alpha as a whole kind of encapsulates this broad vision of interstellar travel. And a future where we might broadcast our message out to the stars. So, yeah, stay tuned. It's gonna be really cool.
yeah. So if you guys don't know about Alpha Centauri, it's the nearest star to our own star, and it is how many light years away?
About 4.
About 4 light years away. So if it were Star Wars, we'd just hop right there. It is not. And it's actually super, super difficult to get that far. The furthest mission that NASA has accomplished so far within our solar system is to Pluto. And by the time the spacecraft got there, Pluto had already been declared not a planet. So hopefully with this Alpha Centauri mission, starting with Alpha and starting with other Starshot initiatives, we'll be able to make it to our neighboring star. And so really thinking about...
Within a human lifetime, too.
Within a human lifetime,
which is
exactly.
Quite exciting.
Traveling extremely fast. And really, so we're thinking about what we would want to communicate to our nearest solar neighbor. And so we don't know if there's alien life there, but we know there's alien life in the universe, most likely. So that's what the thought of was for the original golden hologram, or the golden record. If you haven't heard of that, it was a compilation of all sorts of different sounds, images.
Generated by Carl Sagan here at Cornell. For a long-term space mission out into the stars. And so if an alien life species were to find that spacecraft, they could figure out how to play that record, and we really tried to do something that could maybe be figured out, decoded, like a record, instead of something more digital. Provide kind of things that one could intuit would be the universal foundational elements of the universe. So like a star map or mathematical equations, stuff like that. But on holograms, it's a bit less ambiguous. It's a bit less ambiguous right now, because you can literally show them, images, right? So if they have the ability to receive photons, then they'll be able to kind of interpret what's going on here. So it's a big step there in that regard, and also in actual kind of data density itself. You can fit a lot more onto a hologram. You can fit videos, basically anything. As C mentioned, it's essentially an infinite medium of storage, if you can produce things optically small enough. So I wanted to update all of you on the status of our payload right now. We have just cracked the 10,000 meter barrier, and certainly have a long way to go, but we're making progress and are sticking to our flight path remarkably well. So once we get live footage from the balloon, which is actually coming from the top of Rhodes Hall at Cornell University, right around here, we'll get back to you very shortly. Also, these didn't quite make it into the live stream, but we have a little 3D mock-up of our payload. We can go even closer, perhaps, if it's a little finicky in Google Earth. And we'll show pictures of everything and some videos that Mike has made. But basically, you can see everything here. It's all suspended quite nicely. So, Eleanor, you want to go over this briefly?
Yeah, so the upper payload is actually part of the Ham Radio Club Amateur Radio at Cornell, and the lower payload is our alpha mock-up. So it does include all the flight boards that our Alpha CubeSat actually does include, and it will also deploy a solar sail. The only difference between this and Alpha is this one is suited with a lot more cameras that you could not bring to space.
Right. For many reasons.
Yes, yes. And it comes with a lot of padding because this one will land. So we have a heater in there. We put some one of those chemical hot hands pouches
right?
in there.
We need a lot of hot hands in Ithaca, so they're easy to come by.
And let's see. I guess if you can maybe put it against something with better contrast.
I will make an attempt.
You can see that there are 4.
Okay, there we go.
Yeah, there we go. So you can see that there are 3 pieces on the outside sticking out, and those are actually to balance our payload. So we're going to be experiencing a lot of atmosphere on the way up, so it will be super, super shaky. By the time we're actually going to launch, it's going to be a lot more mellow, but we do need some way to, in lieu of a gimbal, to settle everything, to get some actual imagery of our payload deploying. So those are going to be used to stabilize the payload as best as possible, and to keep it from spinning around. And then let's see.
Yeah, we do want to clarify that in the event that basically we can't pick anything up on stream, we'll still have really, really great high definition video later for you. So no question about it. We're gonna make something really, really beautiful out of this. Yeah, because we have this crazy camera array on board. Have we received another positional update? Not quite yet. So sometimes they come in relatively frequently. Sometimes it takes 5 minutes or so. But we'll keep you updated there.
Yeah. So as far as what the CubeSat is emitting, it has a rock block on board, and rock block technology is incredibly cool. We're actually going to be bringing that to space as well. So it uses a satellite of receiver stations on Earth, and you can emit the signal in space, and one of the satellites, I guess they're not on Earth, one of the satellites will pick it up, ping it down to a station on Earth, and we'll be able to get it right at Cornell. So we don't have our own antenna that's going to be communicating with the rock block. It's actually going to be pinging to a rock block station, and then back to us. So it's awesome technology, and it has a really, it can be emitted for quite some distance. And so that's what we're going to be using today, and
testing.
Data,
right.
And testing, yes. For about every 10 minutes, we'll get an update from our CubeSat that gives some status updates like temperature, the status of the light sensor that we have on board that tells us if our sail has been ejected or not, and some other vital signs. So we will, once we have launched, it will say that it has experienced the fire command. And so data like that will come back to us at our Cornell ground station. And let's see.
We're getting some videos.
Are we gonna get some videos
all loaded
about
that
Mike's?
Mike gave us about the payloads, so that's quite exciting, and we'll maintain the tracking as well at the same time, just for those who are interested.
Yes.
So that will be set up momentarily, starting with actually the antenna array, I believe. Yeah, let's do it. I hope.
And in the meanwhile, just a bit more about the larger mission that we have going on here. So, in basic words, we have a sail that is hit by a ton of photons emitted from the sun. Normally, that's what a solar sail is. Ours is actually a sail that will be hit by a laser potentially, and that laser array
or testing for the potential of laser transmission, because each element of the technology readiness demonstration can be done sequentially. So it's yeah.
Exactly. So especially in space tech, because everything is so high stakes,
so hard. Very risky.
It's all so high stakes and it's all very expensive. In the college level, it's not as high risk, but we're still flying on a rocket, and we have our rocket spot. So it is really
we'll be flying on a Falcon 9.
Yeah.
We're not exactly sure which one yet, but it will happen by the end of the year.
Yes. So even if the technology on our Alpha CubeSat isn't millions of dollars, actually getting it to the ISS for launch is a huge cost, and so everything has to be perfect.
Thankfully being supported by NASA. We really appreciate that. Thank you,
NASA. And so our CubeSat will be sent to the ISS from the Falcon 9. Is it Falcon 9?
Yes, aboard a Falcon 9.
Aboard a Falcon 9.
Yeah, and then it will use the NanoRacks deployer, which is kind of our commercial space collaborator, to actually eject the CubeSat out into space, and hopefully far away enough that when we deploy the sail, it will not be a problem. Obviously, we've been in discussions with them for many months about this issue, and it's being resolved. So.
Yes. NASA is very reasonably concerned that we could eject our sail, and then it, at the time of ejection, is moving at the speed of orbital velocity, plus a little bit extra.
Right. Well, they just don't want in-space collisions because it's difficult to track something so small.
Exactly. Plus a little bit extra. So especially with
so close to people in space, they want to be cautious.
Especially with our astronauts in space,
right.
Very, very high. Let's see, they have high HR value.
Yeah, that's one way to put it.
That's what you could put it as. We don't want to hit their home with a light sail. And so we have had many talks with NASA throughout the year to make sure that does not happen.
Mm-hmm.
So we have a timer on board that goes for right now it goes for 30 minutes.
12.
In reality, it will be going for 12 hours before we are able to
actually
technically deploy. Yes.
And we'll show you some videos of what deploy looks like as well. That's quite exciting.
Exactly.
Still no updates.
Interesting. We've had plenty of tests to make sure that timer actually works at space conditions. So we have a vacuum chamber in our lab here at Cornell, and we can bring that down to a very cold temperature using liquid nitrogen and very hot temperatures using heat lamps. both in a vacuum condition to simulate the conditions of space. So when we have that timer going and when we have the entire system in these harsh conditions, we have to make sure that the timer is still functional, and to make sure that it prevents us from launching even if something goes wrong, and the sail were to be accidentally deployed. And let's see.
All right, so Museum Maker asks a question. How do nanosats deorbit? It's a great question. So at this point, they generally just burn up. I know that's probably not the answer you wanted, but they don't have enough heat protective plating or deorbit retro thrusters, retro boosters, whatever you want to call them, to actually slow down and avoid just the heat buildup that comes out from re-entering the atmosphere at massive speed. What's interesting is that theoretically, if you have something that's actually smaller than a nanosat, so maybe the size of a speck of dust, it might be able to re-enter, like the smallest meteorites that you find on Earth, because everything that's too large and has too much mass generally either makes a massive impact or just burns up entirely. Yeah, I hope that answered your question, but feel free to follow up.
Yeah, so a quick follow-up. These chip satellites are actually built to have the potential of being sent to a different planet, and different planets with less atmosphere than our own, and be deployed above the atmosphere and settle down, just reaching a pretty low final velocity as on their way down, and survive the flight from outer orbit to the surface of these planets. And in this way, we could get tons of data in different data points.
We just got a big update.
Got a big update.
We're now at about 50,000 feet. Very cool.
Hey.
Okay. On our way. Yeah. So let's get Mike's videos going before.
Let's go for that.
Before we're a little too late there. Awesome. Okay. So we will set that up quickly. Oh no.
So, later in our stream, you will hear from our ground station. So we've got some students working from Cornell, getting rock block data back from the Alpha CubeSat, seeing what's going on there, and then also checking what kind of data we're getting from the entire spacecraft, including images, which will be uploaded through Mike's payloads to us without that much delay. So really, really incredible technology we've got going on.
If it works.
Exactly, if it works. And we will be checking in with ground station in a little bit to see what they're up to and how their GPS trackers are working, etc.
Mm-hmm.
And it also is kind of a mission simulation for our actual Alpha launch, where we will have our Cornell ground station receiving data, making sure that everything is okay. And at the time when all systems are go, we will be deploying our sail in space. And we actually have we have a camera on board of the Alpha CubeSat that will actually be able to send us images from space from the sail deployment. So that will be really, really awesome. And today we'll kind of get a feel for what that will be like.
This is slightly problematic, but we're working on it.
It's slightly problematic. We're trying to get videos up from Mike's payload. So That is the other payload on this balloon. And he made us some videos just going over what instruments exactly he has on his payload, what kind of photography equipment.
Awesome. Yeah. So we'll now kind of present the I guess the receiving station that should be working right now, that we're attempting to get working.
Yeah.
And we'll get back to you shortly. And we'll just as we kind of try and work these things out, we'll show a series of videos from Mike about kind of the whole setup, and then hopefully when we come back we'll have everything working for you. Yeah. So stay tuned.
Today we'll be using the ground station antenna array that's on the roof of Rhodes Hall at Cornell University. This ground station is a collaborative effort between the Amateur Radio Club and the Space Systems Design Studio, also known as SSDS. Sharing this resource is a win for both teams, giving us each access to a great antenna system, while also keeping it better utilized, which prevents it from falling into a state of disrepair. The array presently has 4 antennas installed. The longer 400 MHz antenna is owned by the SSDS and can be used for satellite communications. We intend to use this for an upcoming Cislunar Explorers mission later this year. The other long antenna is a 145 MHz directional beam owned by the Ham Club. The medium-length antenna is tuned to 900 MHz and is planned for use with an upcoming CubeSat mission. We're also using that today to receive telemetry from our low-Ra tracking device. Finally, the smallest antenna in the array is a 1.2 GHz helical. It's tuned to receive the video that we're transmitting from the payload. The balloon payloads are continually beaconing position data, including latitude, longitude, and altitude as they move.
Can't hear him.
We're receiving that data here at the ground station and using it to calculate the azimuth elevation needed to aim the antenna directly at the payload. We'll track the payload across the sky, hoping to get the best possible reception for our telemetry and the video we're using in our live stream.
Sorry about that. We didn't realize that everything was so quiet. We will attempt that again. Yeah. Can you figure out how to set?
To what?
Can you figure out how? Okay. Well, yeah. In the meantime, we'll pull something else up. That's hopefully louder.
This is the chase.
Yeah, much louder. Okay. Here you go. This is discussing the chase computer that he's got on board. I believe his car. He's chasing after the balloon along the flight path right now.
Yes.
This is the chase computer that we'll be using with today's flight. It's a Raspberry Pi with a 7-inch touchscreen display, and as you can see, it has some additional bells and whistles attached. So first of all, we have attached a software-defined radio, which is over here, and this will be attached to an antenna on the roof of my car while we're doing the balloon chase, but for testing, it's attached to a small antenna here. This SDR, software-defined radio, will be receiving signals from the 2 APRS trackers, the ham radio trackers, that we'll be using with this flight. So that telemetry should come in and be received by the Raspberry Pi. It'll be decoded and put on the map, and you can see here that we have information on our map. It'll also send those packets up to the internet through my cell phone tether, and that'll make the position reports that are received from the balloons available on the internet, so the chase teams can use them as well as the live stream folks when they're displaying the website. In addition, we have over here an extra OLED display. It'll also send those packets to just display any balloon telemetry that comes in.
So basically, it's beaconing saying timestamp and altitude.
Reports
and right now we're seeing a whole bunch of beacons at about 325 meters
in altitude, which is about the elevation of my work shack here. This computer over here is another ESP32 device, which is listening on LoRa. If you'll remember, when I talked about our payload box over here, it has a LoRa transmitter, and so it's getting GPS information and transmitting with LoRa at 100 milliwatts on 900 megahertz.
This is a receiver for that. And again, right now I have a temporary little antenna on it. And during the flight, I'll have an antenna on the roof of my car for this one as well. And it's receiving that telemetry, and we can see basically all the same information that's in that display is being received and put on this display. And that information is being received and transmitted to the Raspberry Pi over the internet connection I have established between the Pi and this device, which has internet capability. So the LoRa traffic that we receive is gatewayed and sent to the Raspberry Pi, and also then sent up to the internet as well for display on the HabHub tracking site. So this tracker will appear as W2CXM-10 during our flight. The two APRS trackers we're going to be flying will appear as W2CXM 11 and 12.
All right. Let's get an update on tracking. Let's see. Yeah, we're probably going to get another jump, but we're keeping pretty close to the path here. You can see. Yes, awesome. So, someone had asked, what is a CubeSat, right? So, yeah, do you want to answer that?
Yeah, so I'd love to. A cube satellite is an invention that basically makes space exploration achievable by everyone. And the reason is because it's modular. Every single CubeSat is of the same dimensions, and so it's stuffed in a box. And every single one will be deployed at the same time. And so this makes it so that we're not sending up individual craft after individual craft. We're actually able to deploy about 30 CubeSats at once about all different sorts of missions. And so a lot of schools use it, a lot of colleges use it, and satellites in the past all looked like these giant foils with antennas everywhere. And cube satellites use more so patch antennas and smaller antennas that can be put into this smaller shape. So the invention of cube satellites was really to make space exploration more accessible.
So missions, you're right. So missions have gone from millions of dollars to the thousands of dollars, with Alpha actually only costing approximately $3,000 to assemble. And then you have to factor in launch fees, everything beyond that. It gets up pretty quickly. But yeah, it's basically a 10 by 10 by 10 centimeters, so 10 cube centimeter, hence the cube name, which is about 4 inches by 4 inches by 4 inches open standard, so anyone can develop off of it. And it's since the early 2010s, it's really been a revolution in space exploration.
Yeah, exactly. So each of these CubeSats don't need their own specific deployment system. They don't need a complex mission plan, except for after launch from the International Space Station. The way that they are sent up is in a small block that can actually hold, I think, around 36 cube satellites at once. And so each one, so each one will have the same mission plan, where you have to, where after deployment, you have to have some way of triggering startup. So our cube satellite has 4 different triggers on the posts. Let's see, I need a visual here.
You want me to pull it up?
Yeah, could you pull up the CubeSat?
Yes,
Let's look at
absolutely can. Okay, awesome. So here's basically what everything will look like in orbit. Before we go on, Sebi had asked basically what's the cheapest launch cost a CubeSat mission can have. Well, there are a lot of things associated with actually getting even approval and permission to launch. You got to get a Spectrum license. You got to pass a whole bunch of safety tests and procedures. Right, it's a very risk intolerant environment. So, like ours is basically one of the simplest and cheapest CubeSats ever built, and it was around $2,000 to $3,000. But that doesn't take into account the actual time you spend building it and breaking things, and you need to build stuff again and retest it. And so if you were to actually pay people as opposed to students who work for free to do it, it'd be super expensive. Then on the launch side, I think SpaceX has gotten launches down to about $2,000 a kilogram in terms of like raw payload pricing. Do you know how much Alpha weighs?
Let's see. I don't remember. I think
we're in the 1 to 5 kilogram range, so you can factor in a couple more $1,000 there.
Yes.
Definitely not cheap, but the cool thing about this is if you see these orange things on the light sail here, these are actually CubeSats, and they're the second generation of CubeSats, so they have some additional technology here. I'm going to attempt to get the video again, if you want to talk about the CubeSats on here.
Yeah. Okay, so talking about the chip satellites on the solar sail. So chip satellites are a technology that revolutionizes spaceflight. In the past, we've had these giant spacecraft that need to be put on their own rockets and sent into orbit or wherever they're going to go, to a different planet, etc. Space exploration can actually be achieved by something much, much smaller. So whether it's a cube satellite that is sent to the moon, Cornell actually has a 2U cube satellite right now called Cislunar, if you guys are interested, that is being sent to the moon. But whether it's a cube satellite, a 2U cube satellite, it can achieve incredible amounts of data that once could not be found from such a small payload. So we have patch antennas and different technologies that condense the amount of space that we need on a payload, and we'll get the same amount of data as in the past. So now these chip satellites have an antenna on them. They have an accelerometer. They actually have a magnetorquer, change their own orientation in space.
And GPS.
They have GPS.
Right. It's amazing what you can do on
actually,
these tiny little things.
Yeah, you can put photoresistors, you can put cameras, all on this tiny little chip satellite. So it's like 1 inch by 1 inch or so. Maybe it's 1.2 by 1.2. But they have their own solar panels as well. So they're very independent, small spacecraft. And with that, the options are unlimited, because really you can use one or you can use 100, and you'll still get 100 data points. One moment. We're still trying to get video up, is the scene that's going on. But so if you send these, as I was talking about earlier, if you send them to a planet, you could get about 1,000 data points. So instead of having a Mars rover crawl around for a month to get that same amount of data at different places on a planet, you can get the same amount by just having 1,000 land at different points on the planet's surface.
Right, and they all survive impact. And this has been tested, which is pretty amazing.
So they survive impact because they're so flat and their terminal velocity is so low.
Yes.
Okay. We have some...
And even without atmospheres, they've been shown to survive planetary impacts at crazy speeds, which is pretty awesome. Okay. No.
Wait.
I got sent a funny link here.
I
Okay.
didn't copy and
Okay.
paste the
Okay.
right one.
So, anyways, we're gonna show you a few
There we go.
videos of the light sail being deployed while we try and get this working. So, again, it seems like no one is getting any video feed from our main antenna on top of Rhodes Hall, but they're working on it. So.
Yeah, and all the video feed
There
will
we
be
go.
recoverable after the fact.
Right. So we'll post it on this channel and on the Alpha CubeSat channel as well.
Yes.
So not
and
not
we'll
to fear.
We'll put together some snippets of
Yeah.
information.
And it will have cool music too, which this one doesn't, unfortunately. So. Yeah.
Exactly.
Awesome. So this is actually quite an explosive sail deploy here. That we're excited to show you.
Yeah. So this will show the launch of our solar sail
Yes.
on the CubeSat.
3, 2, 1. So we'll show that again. It was quite dramatic. But yeah, this is basically what it's going to look like in the stratosphere today. Yeah, and so if we bring it back to this part here, you can see that the door is actually on a hinge. It happens very, very quickly. But the door is on a hinge. Probably not. Yeah, okay. So you see the door opening. It's on a hinge that's locked. And so you want to talk about how the door actually opens? It's a very complicated process.
Yeah, I would love to. So we use burn wires for our deployment process. So this is actually a series of 2 wires that are a very strong current is sent through. And because of the material properties of these wires, they heat up super, super hot, and they have a very high resistance to this current. And so when that current is passed through...
Yeah, we've got a whole bunch of these.
Exactly. So when that current is passed through, it gets hot enough to cut fishing wire. And so if any of you have tried to cut fishing wire before, it's not a fun process. Scissors don't do the job very well. You kind of have to like gnaw at it a little bit. But burn wires are a very efficient way of doing this. So we can actually send a signal through our TNC, which is our main flight computer, and send this current through these 2 wires, and those will cut to a series of 2 different fishing wires that are keeping the latch tight and held in place. And then the latch is on a I wish we had an image of this, but the latch is on a spring. So when the wires are cut, it will spring off the door, and our door will open. And
so what makes today unique is that we'll actually have a view like this without the impediments of a lot of air resistance. So yeah, it will be a lot more like the orbital environment, which is quite cool.
Yes, there we have our teammate Andy Tan.
Yes, he's
and I think that's Joao.
He's in the zone right here. Yes, and previous member of Alpha. Where has the tracking gone?
I think it will send another one momentarily.
Okay. We'll bring back tracking in a second.
So our Cube satellite, once it's launched, goes into this sort of uncontrolled tumble. If any of you have watched, I think, Gravity, the movie, she experiences a stressful, uncontrolled tumble in her spacesuit. And our Cube satellite has its own way of escaping that tumble and getting into that controlled, consistent spin and with a single direction. So as you guys saw in that video that was just happening, it will have a very, very fast spin in orbit, but will be going in a singular direction perpendicular to that spin. So we have Magnetorquers on board that are used.
What's a Magnetorquer?
Yeah, let's talk about what a Magnetorquer is. So a Magnetorquer uses current run through a series of tightly bound copper wire to create a force field. So this field will actually reorient the entire cube satellite. We've got 3 Magnetorquers on board for X, Y, and Z. Reorient the cube satellite based off of the data that we have coming in from our IMU. So our IMU tells us acceleration data, and it tells us data about how our CubeSat is tilted at the time. So using the combination between our Magnetorquers and our IMU, we'll actually be able to escape this tumble. And if you have Magnetorquers, you can look online about how that field is actually changing. And there are a lot of different ways to detumble a cube satellite or other spacecraft. And so this one was chosen because it is sized correctly for this smaller 1U CubeSat. There are other choices that we could have chosen, but this one is probably one of the simplest, and I think a lot of cube satellites go for Magnetorquer reorientation. So yeah, we'll talk.
So there were some questions about telemetry. We're still working it out, but yeah, at the moment, we don't think it's descending. But the last information we've received is the same that you've received on APRS, that it's at 53,000 feet. But that was 20 minutes ago, so it's probably a lot higher. Is it acting? Okay, you want to answer that?
Is it acting against the Earth's magnetosphere? So there is something that's called a I think it's called like a magnetic tether, which is a long rod that extends from a spacecraft and uses Earth's magnetosphere to keep itself in position. So it's kind of like being anchored, if you're a boat, to the ground, but in this case, this long rod is actually tethered to Earth's magnetosphere. So the, let's see, is it acting against Earth's magnetosphere? No, it's creating its own force to reorient itself. And Earth's magnetosphere is going to be picked up by our IMU, but that is actually calculated out, so we can really get a feel for what our CubeSat is actually experiencing, but from the Magnetorquers and from its position and orientation in space. So that it will be calculated out.
Awesome. Okay, so these questions that I'm receiving are from someone who's also my mom, and she wants to know a bit more about SSDS.
Okay.
So, do you want to give the rundown on who we are and what we do?
Yeah, let's go for it. Okay, so SSDS, I encourage you all to check out our website, is the lab of Dr. Mason Peck here at Cornell. So we've got a series of active missions going on. Sorry, one moment.
Yeah, keep going.
Okay, so, we've got a series of active missions going on, including Cislunar, which is a 2U cube satellite that will be sent to the moon. And we have Alpha going on right now, and then we also have Pan. Pan is an especially cool mission.
What does PAN stand for?
Pan? Let's see. I don't know what it stands for.
Something about autonomous navigation.
It stands for P, autonomous navigation. Exactly. And so
we'll
idea...
We'll look that up for you.
We'll look it up for you. But the idea of PAN is creating spacecraft once you're in space So the ISS was extremely modular, and it was put together by a bunch of chunks sent up to space one after the other, and then assembled in the ISS or in the atmosphere. And there are quite a few repairs and additions that are still happening to the ISS.
Oh,
But
yes. Pathfinder for autonomous
Pathfinder for
navigation.
autonomous
So basically,
navigation.
autonomous docking in orbit.
Yeah, so the idea is that you could potentially have many, many different smaller building blocks that find each other in orbit. So they have signals that are sent back and forth in between these two 2U CubeSats, and they're able to dock together based off of that data. Now, on Earth, that would be pretty easy. We have GPS, we have visual signals that they could send each other and really figure out how to orient themselves together. In space, it's a whole different set of dynamics because we've got
Go on.
no direction. And even in orbit, we have like the direction of the magnetosphere, and we know which way is down and we know which way is up because of gravity. If you are in space, if you're in outer space, there's no way to have that same sort of understanding of the space around you. So you can't really perceive where you are as a spacecraft. And so you can send signals back and like beacon, and people can be like, oh, okay, that's where they are. But you have to communicate to each other when there are all sorts of outside factors that are going on, space dust, small particles that move each other, move one spacecraft around just a nanometer or so. That can all trigger the inability to dock to each other. So really the idea of SSDS right now is a lot of smaller spacecraft sort of thinking.
Small spacecraft, big ideas.
Small spacecraft, big ideas. I like to think of it from Big Hero 6. Have you guys watched Big Hero 6? It's a great movie. In it, the villain has gets control of this technology that has all of these little magnets that know where each other are and can connect into different shapes of whatever you can imagine. And it's really treacherous because you could create an entire monster just from a couple thousand of these smaller magnets. So that's what we're achieving here, but in space. And so we could potentially create the next ISS near the moon, something like that. And right now, also, we have a lot of conversation going on about the moon and thinking about how we are going to, in the future, potentially have a permanent base there, or have some sort of sustained exploration our only moon. And so we're really thinking about ways that we could create these giant spacecraft that can't be launched from Earth within a reasonable amount, just because they're so heavy. Yeah. And so we have, let's see, what is our maximum? What is the maximum amount of like tons that we can launch right now from Earth?
Oh god, something around 100.
Let's talk.
Probably.
Probably.
Heavy.
Yeah.
Heavy.
More and more we have capabilities. But
yeah,
also
Starship and I guess whatever ULA is working on for Artemis is probably going to be able to do a bit more. But yeah.
Yeah.
Kind of stuck in the around 100-ton range right now. So.
Exactly. And even then, 100 tons is not enough to bring all this material to. Oh, is this Martine?
Yes, awesome. Okay.
Oh, let's talk about.
So we have a very special guest here. We have Martin, who's a member of the balloon team. So hopefully he's coming in to give us an update. Welcome.
Yes. Welcome, Martine.
Welcome, Martin. How are you?
Hi, can you hear me?
Yeah, how are things at outside, I guess?
Where are you, Martine?
Well, right now I'm actually set up outside one of the dorms here at Cornell, trying to pick up a signal from one of the chipsets that we're testing on the payload.
Awesome.
Awesome. Any success?
Yeah.
Can you hear us?
Can you hear us?
Are you having any success?
Yeah, I can hear you now.
Any
great.
success?
Unfortunately, I haven't been getting any data aside from just the normal noise that the antenna picks up. So hopefully, we're hoping that the balloon drifts closer to my semi-low powered antenna, so I can hopefully pick something up. But we have a couple of the guys sort of between me and where we launched with a little larger antennas that are hopefully the main source of data. But at least from my side.
Can you show us
I'm
your?
just out here, kind of in the
antenna?
in the clouds and not really getting any data. Yeah, let me see if I can get the screen share going.
Screen share and screen shares. Oh my goodness.
So this is the. Can you see this going?
Yeah.
So right now what we got going is just kind of noise. We're focused in at the 915 megahertz, which is what frequency the CubeSat transmits in. Um, 915, but obviously there's absolutely nothing aside from just noise.
Oh. That's unfortunate.
So tell us about the antenna that you're using to pick up this data.
I can actually stop sharing and show you the little antenna I've got.
Great.
Let me get my camera going again. Oh. So it's a little omnidirectional antenna connected to a radio to USB hookup, and basically I just have to hold this up and keep it pointed roughly in the right direction, and since it's omnidirectional, it can pick up signals from just about any direction aside from below it. So anything around me sending out any kind of signal I could pick up, but right now since I'm focused in on the 915, I'm only listening in for our chipset, and unfortunately that's still quiet.
Okay. So if we don't get any data now, will we be able to recover it later?
Well,
Oh no.
so the chipset will probably log the data it sends out, but this test is hoping to get this signal. So a big part of it is just getting the signal, and if we don't get it, the test won't be successful. But again, I'm just one of 2 or 3 people sort of spread out along the path of the balloon, trying to pick up signals from this chipset. Obviously, the chipset, as you showed before, is really small, right? So its antenna is not very powerful. So hopefully, a combination of better positioning, larger antennas, and potentially better weather might give us a stronger signal. But I'm not the expert on that.
Right. Today wasn't completely optimal in many ways.
Yes, cloud cover especially, even for the rock box signal, we've been having some trouble on cloudy days. So if the antenna is small, I'm not expecting too much success. But
Yeah, and to our audience, we were really on the cusp of go no go today. So the fact that things aren't working is kind of we're working on it constantly. We've got like a team of half a dozen people trying to figure this out right now.
Yeah.
So yeah, hopefully we can get you something by the end of the stream. We're still, since we started late, we're still not quite at apogee. Whatever telemetry is telling us. So hopefully we can get a signal before then.
Martine, could you potentially pull up something about your design for the payload and how you made those design choices?
Right now I'm actually on a loaner laptop outside, so I don't have any of my documents with me. But I can certainly talk a little bit about what went into the design. It's actually Ben's laptop that I'm using right now. Yeah, mine died a couple days ago. But yeah, anyways, the design of the payload was mainly to facilitate the deployment of that sail. That is definitely the main mission. Although right now I'm trying to get data from the CubeSat. That was sort of an additional aside, since the CubeSat is completely independent and completely separate from the release mechanism of the sail, right? So right now out here, I'm just trying to get a signal from the CubeSat, but the payload itself was designed with those 3 scoops that we showed earlier in the live stream at the bottom, mainly for stabilization and so we could get interesting angles of the sail deploying, right? So the 2 biggest design issues with it was trying to fit as many cameras as we could and not impeding the launch of the sail. So basically, I designed the scoops, and there's a horizontal beam on the top of the box with cameras on either side. At one point, we were thinking of having a camera suspended on the payload above ours, trying to get a shot from above to below. So, like in total, we have I think 5 cameras. One of them's a 360 camera, so hopefully we'll get some good shots with that. But yeah, the design of the solar sail sort of deployment mechanism is obviously strongly inspired from the CubeSat deployment mechanism, since we are trying to do sort of a systems test with that. So I took a lot of the design work that's already been done for, like in previous semesters, and just wanted to try to test it, obviously, much further up. So the design is based around a styrofoam box to try to insulate the sail and keep it warm. A big issue with this sail is that at lower temperatures, it'll fail to deploy, or it won't deploy as smoothly. Like the spring action that we've seen before gets a lot weaker the colder it gets. So we tried to insulate that pretty heavily. A lot of the design was trying to keep that warm. So we have those hot hands we mentioned before, trying to keep that sail warm. We have electronics inside the payload box also serving to keep the light sail warm. We have insulating tape all over the payload. So temperature was also a really big design consideration. I wish I could show you the 3D model I have back home, but you'll have to take my word for it, and hopefully some videos after the fact of how good it looks.
Yeah, for sure. When we pick up those videos, we'll be sure to tie in some photos of that 3D model to really explore the design that went into it. Okay.
Bizarre.
Let's see. So we're not getting any more updates from our balloon.
No more telemetry. But we are going to get someone who has been in conference calls with Mike right now, who's on the road chasing the balloon. If you see his most recent update was here, you can see his little car.
So he has to skirt the lake.
Right. He has to drive all the way around the lakes where the balloon can just cheat and fly over them. Yeah, so Martine, we're going to get Lauren in here. Thank you. Good. Best of luck.
Awesome, yeah.
Yeah.
Thanks, guys.
Awesome.
All right, goodbye, guys.
Awesome. Okay.
And, let's see.
Cool. Okay. Let's get Lauren on the call. Okay. Yeah. So while we wait for her to join.
Yeah, so
we had
let's-
a couple of questions in the chat. Okay, so a lot of people are talking about antennas. Yes. Yeah, I think the problems that we're facing today go a bit beyond AIM. I feel like it's software based, and we'll have
Yeah.
Lauren on to diagnose that.
Yeah, we've had
yeah.
our software system.
Right. Just a bit of moisture in the air could change the outcome. Exactly.
Yes.
It's a very good point. Okay. So let's get Lauren on.
Awesome.
Hi.
Hey, Lauren.
Oh.
Hi.
Hi.
Hi. So I am just talking to Mike, who is in the chase car. Just trying to work out what is going on with all of our multiple GPS. Yeah.
So what's going on? you have any
Yeah,
more
so give us some
information than we do?
So not really sure. We haven't gotten, so the rock block is the iridium transmitter that we have on board. We have not gotten any data from that since 309. So,
Wow.
but we have uplinked the message to deploy. So we'll wait and see. I guess our hope is that our GPS on board, our payload, does have data and will deploy at the hard stop we coded in.
Okay,
So.
and what was that hard stop for all the viewers?
Let me look.
Was it
Pulling
something
up
like
the code.
Around 90,000 feet?
Yeah, it's around 90,000 feet. It's 89,062 feet.
Oh, that's a lucky number.
Wow.
Good to hear.
So how did you choose
Yep.
that number?
So Mike did a lot of calculations based on the weight of the payload. Just to see, because there's like a whole sequence, like in his payload box, he has like a camera that can actually flip up and down. So that camera flips down. We wanted to give time for the rock block to attempt to uplink the command so we could manually deploy. And then this is just, like right before burst. We want to give it a chance to deploy.
Okay. Have you heard anything about the kind of getting information from roads? Because I understand that it was working initially and then...
Yeah, so I'm TCP'd into that. We're not getting video from roads. I'm actually going to call Mike back and SSH into another box after this and just try and work out what's going on. So I'll probably go do that now. But it was great talking to you guys.
Yeah.
Yeah.
Thanks for joining us.
Hopefully we can talk to you more a little bit when you're less busy.
All right.
We'll see you.
Yeah. Bye.
Yeah. Okay. Bye.
Okay. Yeah. So.
Awesome. So
you can see, everyone's a little frazzled right now.
Lauren didn't have any time to introduce herself, but she is actually a freshman at Cornell.
Very impressive freshman at that.
A very impressive freshman. She did robotics in high school and came to us with a lot of skill and willingness to learn. So at this point, she is pretty much taking the lead on the flight code that we have. So our mission got
for the entire Alpha mission.
For the entire Alpha mission, exactly. So she actually came into our team on the balloon team and actually became extremely useful elsewhere. So our entire mission, Alpha, has been going on in a large extent since 2017.
16.
Since 2016.
Yeah, that was when the first 10 assembled the first prototype over the summer.
Yes.
In a kind of I guess one would call it just hacking it together, or in a building blitz, something like that. But we've had to go through multiple iterative processes to get us to where we are today.
So since,
even then,
yeah.
this
Since that first 10 who did a design challenge over the summer and really got together this concept, we have been using the same flight code, the same basic design since around 2017, and just iterating on it. So Lauren is actually having to deal with that heritage code that is created from year to year from students who could have left, and really trying to figure out what is going on exactly. And so she brought us onto
Right.
GitHub, and she transferred everything into C++. And so we're really developing the flight code to a optimal level of readiness for flight. And so we do have our we have two main issues that we're still working out with our spacecraft. Our attitude control system, those Magnetorquers that I was talking about earlier, still has some coding, some programming problems that need to be worked out. And then also our flight code needs to be debugged in some respect to make sure that it's 100% ready for flight.
But we've made enormous progress this semester,
Exactly.
More than ever before. So
Exactly. And as it stands, our CubeSat works perfectly well on the ground. We're just trying to get it ready for projecting that information back to us on Earth, so that once we have our ground station up and running, we'll be able to communicate with our Cube satellite, which presents a lot more challenges actually than the balloon launch. So we are ready today for the balloon launch to our code readiness, but we are not ready yet for the ground station that will be put together after launch from the ISS. And so that's happening this summer. It's a really exciting time for us. And yeah, largely structurally, from the mechanical engineer's perspective, we're all ready to go. We've had some changes to our flight burn wire setup just to make it a little bit more consistent. And it was consistent before, but everything about space is about absolute perfection and making sure that nothing will go wrong on the day of. So a lot of resources, a lot of time is going into making sure that that level of readiness is there for structural as well as for the programming behind things.
And we don't say that ironically. That's that the amount of testing that has to go into spaceflight is a lot more rigorous than happened here. So
yeah,
yes.
yeah. So talking about testing a little bit. I forgot to introduce myself. I'm the testing and integration lead of Alpha CubeSat. So I forgot my title. I knew there was something I forgot.
Perfect.
And yeah, so our testing sequence for the Cube satellite is. We have
an update.
An update.
Whoa!
We have an update.
Oh, that's.
Oh my gosh.
That's
unexpected.
Well, this could have occurred. Okay. Interesting. Okay,
let's check the angle on
we'll
that.
analyze
Let's see
this.
If it's gone down.
Okay, so essentially, it looks like we didn't get any updates at Apogee up here, and just basically completely skipped that. So it looks like we're on track.
Yeah, so as
maybe
you can
for a
see,
landing closer to lock than the predicted area. So that might not kind of. There's a little airstrip here, so people might not like that. But hopefully it's not too busy. Yeah. Yeah.
See, we're just going data point by data point. So we did reach that apogee, or close to it, as was expected in our flight path. But now we've already made it back down by the time we've got our next data point.
Yeah, which is a little unfortunate, but maybe we can try the landing stream and see if that's working.
Yeah, let's
is
try another stream. Now that it's getting closer to Cornell, there are good odds that
well, this is actually
least
at the
from
landing
the-
site itself, so
yeah,
that's possible.
at least for the landing site, we'll be able to get
Yes.
some
So
video.
another
back.
not anonymous someone who is also known as my dad is asking if we have camera shots from the balloon. This is the problem that we've been trying to diagnose this whole time.
I wish we'd have screenshot it, because before launch we had a pretty nice stream for a little bit, and it is a software issue. The server crashed on us. But we will have all of this video data afterwards.
Yeah,
and
yeah,
we'll be
yeah.
uploading it.
And we'll put it up momentarily. And
For
if
you guys.
if you found out about us, if you found out about us on Reddit, I will be posting updates there as well. So not to worry. Every single subreddit that we hit, we'll have that. If you found out about this on Facebook or LinkedIn, updates will be there too with regards to footage after recovery. We'll get. I hope if he has cell service, we'll at least get Mike on here to give us kind of a rundown of recovery at the end of the stream. So definitely stick around for that, or tune back in for that later. As Kent was saying, it looks like yeah, I mean, it's hard to say, but based on the fact that it's stuck to the flight path exceptionally well altitude wise, based on the data points that we have, we would assume that it hit apogee and then burst. And so what does burst actually mean? Well, we'd be happy to show you, because we have some pretty, I mean, some of you have already seen balloons bursting before, but this is still pretty cool. So yeah, we have something that Mike recorded on a previous launch, I believe with the Boy Scouts, which is kind of interesting. Cool. Okay. Let's see. Okay. Beautiful.
There we go.
Okay, we have it. Awesome. So, yeah. It's a pretty spectacular view. And this is just kind of a TV grade camera. So if you can imagine, we have a pretty high quality 360 degree camera, an Insta-1 360 on board, or an Insta-1X 360, something like that.
Yeah.
So realistically, we're looking at something pretty exceptional. Once we edit it, we'll have 5 different views of the light sail being deployed, and it's just going to be something that no one's ever seen before. So that's pretty exciting, something to look forward to. We can actually show you some more information about how this sail is folded and how it ends up being deployed later, which is quite cool. So we'll get that up for you in a second. Yeah, we're just in correspondence with the team, trying to figure out where Mike is, if he's going to be streaming recovery, so on and so forth. So yeah, sorry about that. Okay, awesome. So do you want to see if we can get Andy Flash?
Yeah, we could.
Yeah. Okay.
I'll send.
So we're going to send a message to the Silicon Valley inventor, and he's invented a whole bunch of toys. He's really into robotics. He's worked at NASA Ames on crazy space research for a long time. He built a jetpack, and he built our light sail. So we're going to see if we can get him on to kind of give us a rundown of what that process looked like. But yeah, this is, I believe, from him. We'll see if it has volume, and take it from there. Great. Okay, it's a slideshow-esque presentation, and then there's a cool video at the end. some of you are noting that the descent is very, very fast, so it looks like we had a burst. Thank you for that information. That's good to know.
Snap.
And another position update that we'll show you soon.
Snap.
So this is the very, very slow-mo sail deployment here.
Slow-mo cam.
Oh, did someone join our meet? Oh, that was the other Andy.
Oh.
Okay, well, we have a second Andy that will be coming on after we show this sail deploy here. Yeah. Hope you found that enjoyable. So we should note that Alpha is completely 3D printed, at least the chassis, which is incredibly cool, and allows us to make it such low cost. Yeah, so who do we have?
And replicatable.
Yes, the idea here is to create kind of an open standard of spacecraft that will be able to deploy smaller things from within them at this you know, CubeSat size standard. So 4 by 4 by 4 inches or 10 by 10 by 10 centimeters. Cool. Okay, let's get Andy in here.
All right.
So Andy is Alpha's chief engineer, and I'm sure he'll have a bit to say about this.
Yeah.
Hi, Andy.
Hey, Andy.
Hi there, can you hear me?
Yeah.
Yeah.
I apologize, I don't have any video on this computer. I can swap over if you like.
Yeah, that would be great. Love to see you. Very
I'd love to see you.
visual oriented today.
Okay, give me a moment.
Oh.
I'm getting. Oh.
So one of our
Okay.
balloon
So
teammates has
yes, she's
started
streaming from landing.
OBS.
What? Okay, we're getting very interesting errors now, so that's new. But at least it's not the same error. Whoa! Whoa! Balloon!
Some snippets.
Yes! Okay. It's coming in.
It is
Kind of.
It is broken up, but we are getting some video footage.
Hey! Balloon footage! Don't say we didn't get it for you. Yikes.
Let's see where it is on the map. It's coming down to. Right now, it's above the
Yes.
yard.
Okay, so it's significantly deviating from the expected path as it gets further
Can you
down.
tell us altitude right now?
Yeah, I mean, the actual video shows the altitude, but we're looking at least from the last APRS update, approximately 20,000 feet.
Okay.
This is streaming from, again, Sam, who is a member of the radio club, and she's just picking it up on her phone, I believe, or using it. It's again like a mobile antenna array.
Yeah, this is awesome.
But if this is the type of signal we're receiving at low altitude, then certainly we would definitely have problems higher up. Wow, that's the payload. Okay. So we'll see if we can spot the sail down there. It's getting whipped around pretty hard. Altitude is 4,848 meters.
Awesome.
Again, a solid number. Oh, dropping precipitously. But wow, okay. This is like landing on Mars, ladies and gentlemen.
Is it switching in between camera views, or?
I don't know.
Is that just...
Payload is alive. Yes, everyone's very excited.
Martine from earlier just sent us that the payload is alive.
Though we can't really make out just yet if the sail has actually been deployed. Hopefully, as we come through the clouds, that will become more clear, because the camera is a payload on top of a payload. And the way we looked at it in Google Earth, it didn't really do justice to the type of separation we were looking at. Yeah. So thank you for sticking around. We hope you finally enjoy a little bit of balloon footage, if it doesn't make you a little bit nauseous.
Yeah.
Yikes.
If only the balloon were large enough to bring us all up.
Yeah, but you know, even in the Finger Lakes area, we're providing a little bit of sunshine on a cloudy day. So we hope you enjoy that if you're joining locally.
Yeah, and so this one is black and white, but all of our cameras that are the alpha payload are colored.
Mm-hmm. Yeah, we got 3 action cams, and again that Insta 360 cam, which is going to be so cool. It was recording at, I believe, something like 3,100 by 1,504 at 100 FPS. So we're going to get even slow-mo deployment, which will be fantastic. Yeah.
Yeah, and we also have our 360 cam on board, so we will be putting together something that you can experience
in VR.
In VR.
And we're gonna have a VR showing, because I think everyone's gonna.
So we're all excited to see that.
Mm-hmm. Yeah, we put a 256 gigabyte SD card in there, so hopefully that was enough. And for the other action cams, because it might take, you know, if he has to trek through the woods to find this, hopefully that's not the case. But it might take Mike a little bit of time to actually access the balloon post landing, and so if the cameras die, we're not sure if, you know, they'll just completely wipe themselves. So we've been like blocking the videos into 3-minute chunks to make sure that they survive, because we really want to get this sail deployment on video. So yeah, whether it's now, which obviously is not the case, or you know, today or tomorrow when we upload it, we're super excited about that, because this has really never been done before.
Yeah. And after this test, we'll be ready to. This test actually happened after the entire testing sequence for our Alpha CubeSat. We had a series of cold tests, hot tests. A vibration test is coming up, where you put it on a vibration table that simulates the launch of the rocket. So as a payload on the Falcon 9, it will be experiencing similar vibrations, frequencies to what we'll put it through to test.
How hard do things vibrate when they get launched in rockets?
Very hard. It will be pretty incredible to see that test happening, because it is the last test that our CubeSat will experience before launch. So our partner Nanoracks will be taking our payload and bringing it to the testing site, and then delivering it right to the launch. I'm not sure if they have a place that they keep everything before launch, but the launch site, and then in a month or so it will be launched, and then we'll get the signal.
A month or so after we deliver it.
Afterwards.
Yes. Not in a month, unfortunately.
No, not in a month from now. Mm-hmm.
We're looking at October, November, December.
Yeah. So we're looking at the timeline of how everything goes after that final test. We also actually put our CubeSat under a structural test. So
what does that mean?
So that means putting in NASA, for NASA missions, that means really trying to pull apart the CubeSat in all sorts of different, or the mission in all sorts of different ways to really test its structural integrity. For us, that really just meant clamping down on it in various ways to make sure that it is structurally sound. Because we are choosing a pretty untraditional route of 3D printing our chassis, out of bluestone, if anyone's wondering about that.
It's a really high-tech, strong kind of plastic-esque material
Yes.
that looks blue.
And it's
Yay.
blue. And so the video you guys saw earlier with the tan CubeSat, that was actually an earlier version, and it even might have had the springboard inside. So earlier our payload was launched, or our solar sail was launched from a little springboard that came out when the door opened. So it was a series of spring and a smaller platform that pushed the sail out. Now it is that that spring wire that Andy Philo designed
The
for us.
inventor. We're getting our Andy, which is
Yeah, so
still an engineer. Still an engineer.
Anyways,
yes,
yeah, let's
very
hear
accomplished
from,
in his
let's
own right.
hear from Andy.
Awesome.
He's ready to go.
Welcome, Andy.
Hey, Andy. No visuals.
Hi, can you hear me now?
Yes. Oh, awesome.
Hello.
Nice to
Okay.
see you.
This is working?
Yeah.
Yes,
Okay.
you are on live
Hello.
stream.
Welcome. So you wanna introduce yourself and tell us a bit about what you do for Alpha?
I can see that. Hi, I'm Andy Tan. I'm the chief engineer of Project Alpha CubeSat. I joined the team when I was in freshman year, if I'm correct. And initially, I was involved with the testing of the CubeSat prototypes, specifically the one that you saw. And it's just been a fun ride since. What do you guys want to know? I'm also spotting the live stream from my other computer, but yeah.
Can you tell us a little bit about how the CubeSat has evolved over time?
Right. So this project originally began in 2015, and Joshua has done more historical research on this than I have. But it originated as a CubeSat competition, which a high schooler from Ithaca High School had won. Professor Peck funded it with,
her name was
again, the
Isabel
details
Dawson.
escape me at this earliest
Thank
stage.
you to
I was
Isabel
not here
Dawson.
yet. There we
It
go,
was-
yeah.
It was a science fiction writing competition sponsored by the
Oh.
Museum of Science Fiction.
Yeah, it first started as I believe it was called New York CubeSat 2016, and they had a bunch of interns and other Cornell students come in and work on it over the summer, which created the initial prototype. And this initial prototype actually featured a very different architecture than the one we currently have. It utilized two microcontrollers, one primarily to run its attitude control system that helps us determine the way we're pointing and the way we're rotating in space, and then the other one managed everything else, which was the deployment, the power coming from the solar network, and then the current sensors and all the safety functions we have on board. This eventually changed when we changed over to TC 3.5, which is capable of running both systems at the same time. And as such, the work kind of multiplied as we tried to convert into this new system. It's now 2021, and we have finished the majority of our flight phase construction, and we're looking forward to delivering and launching in the next year. But yeah, I'm very excited and very fortunate to have joined this project when I entered Cornell.
Awesome. So can you tell us kind of what might have been the biggest challenge that you faced with Alpha over the last few years?
Ooh.
I mean, there have been many. I know.
I'm gonna blabber a bit so I can think about the biggest challenge. But well, yes, that's precisely what I want to emphasize, right? Alpha CubeSat has not just been a single large challenge; it's been challenge after challenge. And one of the things that I appreciate the most about the team I work with is that they're willing to tackle every challenge as it comes, and they have the initiative and momentum to do so. And I haven't really seen anybody frustrated. I've only seen enthusiasm and a positive outlook on the CubeSat. And I see people And I want to thank them all again. And we want to appreciate and recognize the researchers who came before us in those few years that I wasn't here, and all the hard work they did. We're on the shoulders of giants in terms of the code, the structure, the design overall, the deployment mechanism, all the communication with NASA. I suppose an ongoing headache, however, is communication and documentation, if you will. And so one of the greatest limitations of long-term teams is the ability of each generation of its researchers to pass on knowledge to the next. Cornell has some intrinsic systems to do this. For example, the end of semester reports are supposed to help educate the next generation of researchers exactly what the previous generation had done, what they were supposed to do, and what is the remaining, and what is their recommended courses of action to finish those projects. However, this doesn't always communicate smoothly, particularly because the skill set of each researcher that joins our team can be vastly different. And so we did lose a bit of time and effort with regards to not documenting everything or simply not being able to understand. But reaching out to the previous researchers post-graduation has proved very helpful with this. And we're still going full steam ahead.
Awesome. Yeah, we just got confirmation actually from a viewer that the package has landed. I don't know how they determined that. If you want to put that in the chat, but that's quite exciting.
Yeah.
So we've been tracking the package, and Mike, it looks like he's on a beeline towards towards the package. So towards the payload. So hopefully we'll see that very soon. I don't know if we have a scale here to determine exactly how far away this is. The altitude, our eye altitude is quite high still. So I'm not quite sure. But if it landed around Venice Center, or Scipio Center, I guess we'll figure that out.
We're trying to figure out if the payload actually deployed, if the light sail deployed.
Yes, which means if it didn't, we'll be doing this again. So, yeah. Okay. Yeah. Right. I'm not sure who said it landed. But we're still waiting to get confirmation for that on our end. Right. Yeah, we stopped getting video output, so we're still waiting on all of this.
And another viewer has said that it's still 14,000 feet.
Right, which is what the tracking information says. So we'll see. Yeah, we don't know.
So there are a few things that had to go correct for our light sail to deploy. One thing, there were two methods for deployment. One was our ground station would send a message around apogee to the rock block, and the rock block would talk to our flight computer, the TNC 3.5, and activate the deployment sequence. And because we wanted to have double the chance of actually mission success, we had a second trigger that was GPS locking. So when the GPS read of a certain altitude, it would automatically trigger the TNC 3.5 to trigger the launch sequence. And if neither of those things happened, if the rock block did not receive the signal that we sent, or alternately, if the GPS did not get lock on its position, we might not have deployed. And looking at those images, we didn't see a sail flapping around So there is quite a good chance that when we gather our payload, we'll find that it has not deployed. In which case, we'll go for a second launch and retry, maybe add a third level of making sure that mission making sure mission success happens, and maybe that's GPS lock, a second GPS lock, or a different rock block trigger. But let's see. We're still trying to confirm if it has landed. Do we have another data point?
Did you pick up on this? Yeah. So the nice thing about farmland is that it's easy to recover, but the problem with farmland is that
it's private property.
Right. Yeah. You need to get people's permission before you go there, which is, it sounds obvious until you try and actually figure out how to do it. Some people might not be home for a while, so
yeah. So we chose our launch spot based off of predictions of the weather, of wind conditions that were monitored today, and all week long our predictions have changed. So
basically every few hours.
Basically every few hours, yeah. So today we decided to launch. We went for the launch despite the weather. It's actually looking sunny now. But we did have to have good light conditions too.
Remember, it's pretty far away. We're we're kind of down here, and this is
a little bit further north.
By estimation, basically 20 miles away, something like that. 20, 30 miles away.
Yeah. So earlier this week, the prediction was a lot longer of a flight actually, up from the launch spot would have had to be a little bit further north for it to land closer to Cornell, and we also don't want it landing in a lake.
Right, and we kind of have to thread the needle between different airports here. It's a relatively rural area. If you're not familiar with the Finger Lakes region, it's quite cool. I can give you kind of
it's quite beautiful.
Okay, this is not the right orientation. Let's do north up. Okay, there we go. Right. So here we are in the United States, and then if we zoom in, we're in the state of New York, and to kind of the northwest of that, right under one of the Great Lakes, Lake Ontario. And then as we go in, you can see that this is our lovely Cayuga Lake here, kind of right under Apogee, where we hope the sail deployed. Yeah, so it's a bit of background.
Yeah.
But a lovely place to be, full of vineyards and the like.
Yeah, the way up was a lot longer than the way down. And if you launch balloons yourself, you'll know how this goes. But our amateur radio club, Mike set this up. He's launched many balloons before, and knows how to keep it consistent, such that the parachute will deploy every single time. And then also just understanding...
We needed a specific parachute based on the mass. So that's also an interesting calculation that goes into this.
Yeah, also understanding how to calculate the estimation. So the estimation of the flight path was based off of flight mass, center of mass, sort of things like that that go into...
And actually... go ahead. There's a pretty cool program that actually can kind of like show you what the calculation looks like.
Yeah.
And without going into too much math, you can see here that in Windy, it's quite interesting to look at while we try and get some additional information from Mike. that basically throughout the flight path, not only are the winds changing direction, but they're also different at different altitudes. And so if we take a look at, say, 10,000 feet, they're suddenly moving south where they were moving east before. And then if we go up to, say, 20,000 feet, now they're moving north, right? And then if you go up to 10 kilometers or 33,000 feet, they're moving southeast. And then if you go up to 45,000 feet, then suddenly everything's moving east. So it's quite an interesting calculation where you have to combine all of these different levels the whole time. And obviously it's difficult to get right, but considering that we landed basically just northeast of the flight path, I believe, that's pretty good. I think we're happy with that. Yeah. Again, it's kind of going in between the airports. We had to file a couple NOTAMs, or notices to airmen, that Lauren took care of earlier. And anything from the team?
No updates yet.
Okay.
We're really trying to see if the payload has landed, and what our update is. Can we get on call with Josh?
Yeah, I can call him physically and ask.
Yeah, let's call him. So Josh right now is on a road trip of his own with the larger antenna, trying to get data from
So basically
that
doing
chip satellite.
Basically doing what Martine was doing, but
but following more closely to the flight path, with the hope of having the best chance of getting that radio transmission.
Yeah, so hopefully we were able to at least conduct some science. That's obviously the goal of this whole thing. That's what makes it so exciting. Found Mike's car. Okay.
We can also track the.
Can you get Josh on the phone, you think?
Yeah.
Send him a link.
Can you?
Or we'll get him in the call, hopefully. Yeah. So Josh is the. Oh, beautiful.
Perfect.
He just joined. Yeah. So
perfect. Thank you, Josh.
Josh is the graduate student and kind of the brains behind the whole operation, but recently he's just been the brawn and picking up on all where work needs to be done. He's incredibly committed, so we're so happy to have him on the team. And I guess,
hey Josh.
Yeah.
What's up? How are you?
Fun afternoon, experiencing rural upstate New York. Some beautiful fields, wineries, Confederate flags, and not so much luck on CubeSat data. Kind of experienced the same things as Martine, even with the more expensive antenna. So I mean, that's a big lesson learned for us in terms of the equipment we might need. It might mean that we need like a preamp or some kind of low noise amplifier. I was thinking just because it's a shorter distance than space that we'd be fine with the current equipment, but yeah, that certainly could be a factor.
Do you think the weather played
So
into that?
around 450, I kind of gave up on that spot. It could be, but again, like this is the first time we're really testing over long distances, so there's certainly things we're still learning here. So since then, I kind of drove to where the original predicted landing spot was. Just try to kind of look up and find a balloon. I was sticking my antenna out the car window, trying to see if I could pick up anything. And then we drove to kind of the more updated drop location, and I happened to find Mike's car, so now I'm chasing him.
So now Mike's chasing the balloon and you're chasing Mike.
I can probably flip my camera around. There's a truck in front of me with a tank.
There he
giant
is.
antenna.
Awesome. Yeah, wait, so he's got
So,
a
yeah.
giant antenna
Hopefully he knows
on
where he's
board
going, because I don't.
on the back of his truck.
Yeah, I'm assuming. How many cars could possibly have antenna on
Maybe
this
let's
area, right?
maybe let's try to
And-
get closer behind him so we can see his setup. Tailgating Mike.
It says U-Haul on the back. I know he rented a U-Haul truck.
Yeah, no, it's definitely
Yeah.
him.
So oh, he spotted us.
Oh no.
The chase of
Spotted.
the chase.
Yeah. So I kept mine, and you might be able to say hi to Mike.
Great.
Yeah. Well, we haven't gotten any position updates. I know that Lauren has GPS updates for herself.
We've been refreshing everything, and someone in the chat said that we landed, but we're not completely sure yet.
I think ground station is
Yeah, I'm
really
not sure
trying to
either.
figure
I'm just
out-
hoping that Mike knows where he's going. He's a pretty deliberate turn.
Yeah. It looks like Lauren's just trying to figure out if the payload actually, if the sail actually deployed.
Yeah.
So.
Sure.
They were getting some rock block data that
Okay, we
they
have
never
definitely landed.
Awesome.
Got the announcement from Lauren at ground station. She's got a GPS tracker in addition to our radio tracker that we see on the map. And so we have stayed at the same altitude, the low altitude of a few feet, for a few minutes now. And so that is confirmation of landing.
All right, well.
So, Josh.
Okay, we have some.
Do you see the payload? Do you have any eyes on it? We can't hear you. Okay, now we can hear you.
Was on mute there. No, not yet. Looking at the last known coordinates, we're near some trees, so that's always promising.
Awesome.
Oh no.
Yeah, we might
He
have
could be
to,
stuck up somewhere.
We might have to hire a tree climber.
So if anyone's interested in the rock block output that we got recently, we'll put it on screen as well.
Yeah, so this is the data from our rock block that is on board at the Alpha CubeSat payload. And so this is one of the methods that we use to launch our sail. And hopefully, based off of, hopefully our CubeSat received the message and launched the sail. We'll actually see that through a visual confirmation, but...
Momentarily. So stay tuned.
So stay tuned, yeah.
At least it didn't land in a lake, so that's helpful.
Yeah, so we're able to send brief codes to the Cube satellite, and we have various codes that we can give it and respond to scenarios that happen during flight. So we are able to put it on standby from ground. We're able to do a few more things to the sequence or to the operating system. Send some messages. Josh, can we hear you?
Okay.
Josh has left.
Josh has left. Okay. Well, while they're working on that, we'll bring in Andy Philo if possible. Is he in here?
Yeah.
Is he in the
There's
chat?
3.
Oh, cool.
Oh.
No.
Nope.
No. Where did I see him? Oh, he's in the Zoom though. Do you wanna?
He's in the Zoom.
Oh,
We've been
Lauren's here. Hello.
Let's talk to Lauren.
Yay.
Lauren, can you give us some updates?
It's a party.
Yeah.
Hi. You got some updates for us?
Oh, sorry. I'm listening to the old live stream and getting the delay. Sorry. So just to give you an update on the rock block messages, I was just going to explain what we got. So the first 3 are like when the payload was on the ground, and you can see the first value is the GPS altitude. So like that 0 indicates we did not have a lock. And then the 2 messages that say MT, and then they have like the 010100, that was our attempt at deploying the light sail. I am not sure if it deployed because you can see that like next message still had the altitude at 0, which means the GPS may not have had a lock when we wanted to deploy, which means that the hard stop may not have worked. And then, but that now you can see that like we're 1,000 feet off the ground in our most recent transmission, which means we're definitely landed.
Awesome.
Okay. Yeah, wait, so what is the 000? That's the initial values. Is that altitude of the rock block?
Yeah.
Okay. Okay. So when
Yeah.
it is...
Or sorry, so it's like the GPS is downlinking rock block values.
Okay. Okay, awesome. Do you have any other...
So it's obviously a little concerning that...
Yeah, do you have any other data that you can share with us?
Sorry, go ahead.
Do you have any other data to share with us that you've just been receiving from ground station?
I do not. Nope, this is it. I just got another message actually.
Oh?
So it says that we're at 973 feet is the latest altitude.
Oh, so do they come in with a certain delay then?
Does this mean they're pulling it out of a tree, maybe? I'm not sure.
That'd be a tall tree.
Yeah. Like, we're only getting them, like every 10 minutes or something.
Okay. So, and what do you think what is the local altitude? I guess we can get that in Google Earth. So, the local altitude of the anticipated landing site is approximately 1,000 feet anyways. So that's...
It's probably like 900 feet. It's probably 1,000, yeah.
Yeah.
Okay.
Okay.
Okay,
Yep.
yeah.
Awesome.
So...
Yep, so I guess we'll find out and see if it deployed.
Can we get Josh back in here?
Yes.
See some visuals?
Yeah, I can message him.
Yeah.
I'll head out.
Bye, Lauren.
Bye.
Thank you for talking with us.
Okay. Or we could get Andy. Other Andy.
Andy Philo?
If you...
Andy Philo hasn't...
well, if you want to
responded
speak in the Zoom, then maybe we could get him on. Thank you again for joining us. Yes, 973 feet above sea level. That's ground level here. It's like you've got slight plateaus and then valleys that head towards the lakes, which makes for some really, really nice sunsets if you can get on top of them. Yeah.
Awesome, yeah.
Are we...
Hey, Andy Philo, are you able to get onto a call with us? Let's see.
Okay.
We're on a separate chat with Andy Philo.
Yes.
He might not be here.
Oh. Hi. We sent you a... oh, shoot. Hi, Andy.
Hey, Andy.
We sent you a Google Meet link in Slack, if you could join that, because that's what all the viewers see. Loving the background.
Okay.
All right.
Okay, so we'll see you on that Google Meet link.
Yes, so am I out now?
No, so we sent you one.
Oh, sorry, I just lost your audio. Say again, please.
We sent you one on Slack.
Oh, yeah, go to the Slack link?
Yes.
Yep.
I got it. Okay, can you try that?
Awesome. Yeah, so it's in a tree? We don't know. We're waiting for visual confirmation. But it seemed like our chaser of the chaser was trying to figure that out. Obviously, they did get out of their vehicles, so that must mean something.
Yeah, can we, let's see. See about any updates from Josh. Josh was the chaser of the chaser.
Right. Josh, our grad student chasing Mike.
Okay. We're just trying to get some visuals now, get our eyes on the payload. And it might be in a tree. We'll see. We do have Andy Philo who's going to come up here. He is our community partner for SSDS. And
yeah,
has
he's
worked with us.
literally been with us since the beginning. He was kind of supervising the work that was done in 2016 on creating the very first chassis, and then has developed his own light sail at home, which is pretty amazing that we're actually going to be deploying in orbit. And we were talking about holograms a couple hours ago now. It's been a long stream. But he has actually created some holograms of his own. And so he, all of this is kind of I guess celebrating the success of Voyager and its golden record. And so what better hologram to have than a golden Voyager hologram on our light sail, kind of symbolizing the road to the future. Oh, Josh said he can be on in a few minutes. Fantastic. Yeah. So once we get Andy on, he confirmed. He's coordinating with Mike right now. Beautiful. Okay. So, I guess that means something.
That means a lot. Okay.
Okay. So if Mike got out of the vehicle, chances are good he picked up data from the package and direction on it. KA9 SCX, are you affiliated with us? We're not completely sure based on your username.
Yeah.
But it seems like you have a lot of information that would be very valuable to share.
Thank you, KA9
and if so, hop on the call too. Has Andy figured it out, by the way?
Let's see.
Andy has created some really incredible stuff. Oh, he's here.
Okay. Awesome.
Yay! Oh no, it's Josh. Okay.
Hey, it's Josh.
That works. Hi, Josh.
Hey, Josh.
Hi.
What's the update?
We are on the road again. So, our rock block, as Lauren mentioned, started transmitting again. Right. So we're using that data now to actually track down the whole payload. So I just fed it over to Mike, and we're following him. He put the GPS coordinates into his onto his navigation system. So yeah, hopefully we know where we're going. It doesn't look too far away. So I hope to have some updates soon.
Okay. Do you know how far away you are?
Probably like 5-6 minutes, something like that. I think maybe a little further.
Okay, that's great to hear. So for our viewers, we're only 5 to 6. Oh, okay, just a balloon person tracking this flight. Interesting how you have really accurate data. That's good to know. Maybe you wanna share your setup. We've got someone in the YouTube chat who knew it landed before we did, so that was pretty cool. Well on you. Or did you just run the calculations? Because that's also very respectable. Let's see. Did you send him the meat?
Yeah.
Yeah. Okay. Oh, wow.
Wow.
That's beautiful. Oh, I really... Oh, Andy's here.
Enjoy.
Awesome.
There's the Confederate flag. Okay.
Don't want to get demonetized.
Hey, Andy.
Hi.
Hello.
Welcome.
Sorry about that. That was a little bit of coordination.
Am I on the right channel?
Yes, absolutely.
Yes, 100%.
You are live for our, let's see, 23 viewers. Awesome. Thank you for sticking around.
Well, it's exciting, and it's really great because this is a super learning experience for everybody. These projects, going from nothing. I mean, we have to build everything, and the ham radio group, everything's built by hand. So this is phenomenal that we got this far in this, and just really exciting. I can't wait to see the video. I mean, whether the sail deployed or not, we're still going to learn an awful lot on this.
Absolutely.
Yeah.
So you wanna tell us about kind of Alpha's conception and the long winding road to today?
Sure. Yeah. No, it was actually very exciting. I mean, I've had the pleasure to work with Cornell and the SSDS group in the past, and there were several projects, and Professor Peck and everyone else there has been, very accommodating, very nice, allow me to do a little bit of mentoring, which is fun. But the challenge was, it's like I was dreaming of a sail. I was inspired by everyone that's been working on sales, and reading all the information, and everything that was presented earlier was just phenomenal stuff. And it was exciting because beginning to look at all this, it's like making small sails. Small sails have some tremendous benefits in terms of the speed they can go and the durability that they have. So trying to figure out the geometry of the sail and how to do all that. And the trick is that, I don't know if you can see this, this was the first CubeSat that I came up with, and I brought along with me to the group as sort of an inspiration point to say, Professor Peck and others have told me we have this much of a CubeSat, a 1U CubeSat, and the CubeSat is the 100 millimeter square format that people use to launch small satellites in. And could we possibly fit a sail in there? And originally I worked with some Mylar and other things. And then as we progressed, the group came up with the idea that there's types of origami folds that could be used. So using that as an inspiration point, I began to work on some things and send it to the different groups, and they gave comments back. And we evolved the sail to where it is today. And there's a lot of really awesome things in that sail. In terms of the technology, how it deploys itself quickly. It's a very lightweight to deploy it, and it's self-deploying. So even if it got frozen, and at first it got dumped out into space as a chunk, the warming sun would cause it to unfold. So there's a lot of cool things in that. And again, getting to this point now and seeing that, if we got to deploy or if we have to do it again, it's exciting. I mean, this is cutting edge stuff.
Right.
Yeah. Can you talk to us a little bit more about some of the other sail missions that are going on that you researched, or that maybe they're CubeSats, maybe they're larger projects?
Yeah, some of them were mentioned before, but obviously there is a lot of interest in sales, and again, this notion that it's kind of cool just to frame this in a little bit different way too. It's like all the energy on Earth came from the sun. Whether it's the radioactive elements that are in the Earth's core or fossil fuel, all the energy and all the material of Earth came from what eventually became our sun. So the sun powers everything. I mean, that's kind of a very simplistic statement, but even our weather system, like, it's funny, we all go to college, and the first question I always ask, it's like, okay, where does wind come from? And wind is basically high pressure cells going to low pressure cells. That creates the wind. But the thing that creates those pressure cells, again, is the sun. So again, the sun has a lot of energy, and the sail is a way of capturing kinetic energy. So the photons, as was mentioned before, photons are colliding with the surface and imparting kinetic energy into the sail, and the sail can actually move. And it's interesting because it gets into all the orbital mechanics And again, this was 400 years ago. This is Galileo and Kepler writing letters to each other. Thank goodness they had Latin as sort of the common scientific language of the day. But they would send letters back and forth, and based on observations and postulations, the idea that you could sail, and when you think about light is coming from the sun, but how do you sail into the sun? So normally on a sailboat, you would have friction from the water, so you could tack into the wind. Mm-hmm. But in space, you actually use it by orbital mechanics. So you're either going to use the sunlight to accelerate into the orbit that you're in, because if let's say your sail is deployed from the Earth, you're still tied roughly to the orbital mechanics of Earth. So as you accelerate or decelerate into the orbit, you will actually go closer to the sun or farther away from the sun. So you can still apply the notion of tacking and go closer to the sun or go farther away from the sun. So it's all really exciting stuff. And even just using sunlight is the propulsive kinetic force. I mean, you can, with a sail that would be a couple meters across and be very lightweight, you can go faster than Voyager. Voyager took many years and many gravity assists going around different planets to get to its final speed. You can, in a matter of, 50 to 100 days, approach those speeds.
Yeah.
So it's this is the practical upshot is you can travel distances like from Earth to the moon in 6 hours at those speeds.
Wow, yeah. So if we were to send an actual sail to our neighboring star, how big would that sail be? What would that mission look like?
Well, yeah, so a couple things is that kind of there's sort of it's the ratio of the mass to the sail size. Those smaller sails will probably be better off, especially if you're pushing them with a laser. Now, if you're not pushing them with a laser, just using sunlight, it's going to be, thousands, tens of thousands of years. Mm-hmm. There. But by using a laser with constant light, and the laser light is very special. It's very densely packed. The waves are nested in each other, so you can get a lot of kinetic energy from those beams. But the amount of energy into that sort of laser, that would be like using the West Coast energy for 8 minutes to push it to that speed. Mm-hmm. It's about the same amount of energy in terms of raw energy that you would have to put a space shuttle into Earth orbit.
Yeah, wow.
But it's exciting that you could get something to, fractionally at the speed of light, like 25, maybe even up to 30%, to go to, a neighboring star, Alpha Proxima, Alpha Centauri. Those types of stars are conceptually within reach. I would say that what we're working on is on a roadmap. I mean, we don't have all the things to get us there right now. But conceptually, I mean, that's the cool thing, is that we can begin to work on pieces of technology. And like I said, just even as a solar sail, the small sail that we're working on right now is exciting because is launches get cheaper. And, the thing that's exciting, is every time SpaceX is doing their Starship, and, they just had a successful landing. But once they get there and they can escape the Earth's gravity and deploy payloads, mm-hmm. Rocket Labs also is working on a bus that is capable of breaking Earth's gravity. So again, there are bits and pieces that allow us to get to those points where we can now deploy into a region of space where sunlight can push it, where a laser can push it. So, yeah. Again, just an exciting place to be.
Yeah, fast approaching.
fast approaching.
So one question
Yes.
people might have about laser propulsion is, how do you deal with the heat buildup associated with that? How do you make sure that a laser just doesn't completely incinerate your sail? What kind of materials and properties have to go into them to make that happen?
Right. Right. Well, in this particular instance, we are using a polymer, a plastic sail. But one of the things is that the sail itself has microprisms on it, retroreflectors. And the retroreflectors are either reflecting light or they're transmitting the light. So the light that it's not reflecting passes through the sail. If this was, for instance, aluminized material, like aluminized mylar or aluminized Kapton or whatever, the problem is that there's an absorption. So the absorption of the aluminum would cause it to vaporize. And the other thing is the laser profiles. I mean, we're in early days of all this technology, and it's long past and long out of memory, but there was a time when steam was an incredible thing. Originally steam was very low pressure, and the steam engines were the size of a house, and they were used to pump wells. And then there was this engineer called Richard Trevithick who said, no, we want to do high-powered steam and make tiny engines, and we could actually make self-propelled vehicles. We could make auto-propelled carts. And he wound up doing that. He died penniless, and he never really got anything into production. But the things that he did with steam, led to internal combustion engines and all of those other things. Mm-hmm. So it was an amazing progression. And that's what we're seeing likewise. The fact that lasers are getting cheaper. Mm-hmm. It used to be when I was a child, a boy, I really wanted a laser, and I bought a 0.5 milliwatt laser, and it was $300. It was a helium neon glass tube laser.
Back then too. So.
And at the beginning of this project, yeah, and I bought 10 lasers shipped for $1.10 that are 10 milliwatts and run off of 3 volts. And they're the size of a pencil's eraser. So Moore's law, as it has applied to other technologies, is also applicable to laser technology. We are seeing higher density. We're seeing newer technologies. We're seeing things like fiber lasers. So they're a cross between fiber optics and lasers, and they can make an incredible amount of energy, very efficiently. So again, these are the steps that are leading us. Oh, and the other thing too, it's like, it used to be like a laser was like, ooh, a laser. And now it's like, well, how many lasers do you own or do you touch every day? It's like every time you buy something in a store and they scan it, it's being scanned by a laser. If you have a CD player or a DVD player, and I know that format's sort of going away now, but those are all lasers too. Lasers have become very prolific, very inexpensive. Lasers for cutting things. It used to be only gas tube lasers. Now there's diode lasers that can cut things. It just continues to get more and more prevalent.
Yeah. Wait, so can you talk to us about the chip satellites that are going on the sail, and really what role they have there? Just as a positioning beacon, or is there something more?
Well, so the CubeSat technology that has been developed at Cornell is very amazing. The idea is that, reducing the size. We talked about CubeSats and how the CubeSat, that something this size was developed, and it's replacing satellites that were the size of refrigerators. Yeah. So something that was measured in terms of meters and weighed, many, 100 kilograms. Now it's a cube that's 100 millimeters by 100 millimeters, and it weighs 1 kilogram. Well, now the actual, this is a sprite or a CubeSat. And, these are, 30 millimeters on a side, and they weigh a few grams. And again, there's a photovoltaic cell on them. There's instruments. There's accelerometer, gyro, optical sensor, and a radio transmitter. I don't know if you can see these little wires coming off of here.
Yeah.
So this particular one had individual wires, and the current generation one has a patch antenna actually built onto the substrate. So this has been very similar to what we have seen with cell phones. The first cell phones were giant blocks, and you had to raise an antenna, and now you can buy a cell phone that you wear on your wrist.
True.
So where do you think,
very similar developments of technologies.
So where do you think you mentioned that there's been a next generation of chipsets produced? Where do you think that will progress in the future?
Well, again, like right now, they're being incorporated on the four corners of the sail as sort of discrete components on the sail. There will be a time when they are integrated into the fabric of the sail. So the photovoltaics, instead of just having a little photovoltaic cell, the sail could have an integrated photovoltaic cell on it. It could have a lot of, it could be the antenna. It could be a much larger antenna to be more efficient. There are things like that, or even for sensing, there can be embedded coils into the CubeSat. That's already been demonstrated. Mm-hmm. And you can use the energy captured from sunlight to magnetically orient in Earth's orbit a CubeSat. So that's pretty exciting.
Yeah. So we had a question about how the sail will actually be oriented, and we talked a little bit about it. But is there past the initial path sent to it by the laser? Is there any way that it can reorient itself?
Yeah.
Or will there be any other method for it to adjust its flight path?
Right, not necessarily our sail, but a future theoretical sail. Would they have any control systems of their own?
Right. So I've been working on next generation sail technology. Mm-hmm. I've been doing it in conjunction with Avery Dennison, who makes the retroreflective material. They've been very great and supportive on all this. The material, instead of just using a regular plastic, and because people love talking about smart materials, the plastic that we use now, it's just a polymer plastic, so it's a dumb plastic. The next generation is smart polymers. And this particular polymer is piezoelectric. So by being piezoelectric, that means it can receive a vibration and generate a voltage, or if you put a voltage into it, it can actually cause it to deform.
Wow.
So you can actually have bendable elements on the sail. So if you have a square sail, it could actually bend panels. And the panels, by the panels bending as they capture light, they can cause the sail to spin on axis.
Awesome.
So you can have a maneuverable sail with sunlight or with a laser and actually, correct. And again, the thing that's unique about these polymers is, first of all, that the piezoelectric polymer has been used before. So when they did the mission to Pluto, they actually used it as a microphone. So they had a panel of the material, and if any dust or particles were bouncing into it, it would generate a voltage. So likewise, you can use it to detect any impingement on the sail. If you're going through an asteroid belt or you're going through the ring of a planet, you could actually detect those collisions and then, say how dense is the material that I'm going through.
Wow.
As long as it doesn't wipe you out, you're going to do good.
Rip it apart.
Yeah. So but also, like I said, the idea that being piezoelectric, also as you put a voltage into it, it can deflect or deform. So you can have little petals that are folding to adjust the trajectory based on the exposure to sunlight. So those little petals, it sounds kind of far-fetched. It's like, well, has anybody done anything like that? But if you've ever had a video projector called DLP, digital light projector, that's actually a silicon chip that is a piezoelectric device that has millions of little deflecting petals on it, and they shine a bright light onto it. And as those little petals deflect, the light is captured by a lens and forms an image on the wall.
Wow.
So that's an example of a smart, micro material that is deformable and deformable for deflecting light. Well, that's exactly what we're talking about for the sail, except we're using it for control of how the kinetic energy is being dissipated by the sail. And that dissipation of kinetic energy means that it can turn, spin, go on its edge. If you knew you were going into a part of space where there was a lot of materials you could collide with, and you're already going at speed, you may want to orient the sail flat as it goes through that cloud of material, so all the damage occurs along the edge. And effectively, if the sail is 1 meter, you have sort of a 1 meter barrier to protect your electronics. Your electronics could be at the far end of that sail as it's going through the debris field.
Wow.
Then our neighboring star, Alpha Centauri, what kind of environment is it? What kind of a flight path? Do you know?
It is largely unknown. I mean, this is literally a new world, and we know about a thing called the Oort cloud. And again, so the Oort cloud is, a cloud of material. And as you go through that, there's potential for collision and damage. So again, being able to orient the sail, and if that, you would have to turn relatively immediately to go, if you were using sunlight to do that.
Yeah.
Or you could use something on board, that generates photons, like a bright LED or even a laser. And the laser, but you would obviously have to have enough energy. And this is also one of the considerations too, as you get farther from the sun, you no longer can harvest sunlight. So now you have to have something like an isotope battery that would power it. So you could actually have a very thin film that has a radioisotope on it, and as that isotope decays and gives off electrons, you would harvest that for energy.
Yeah. So.
And again, a lot of these concepts are actually very old. In the 1950s, they thought of a lot of these things. I mean, the thing that's cool is we now have the technology to realize this process and utilize these materials, and other people have used isotope batteries. For instance, a pacemaker is an isotope battery that lasts for a very long time. You want it to last as long as the patient. So they're low radioactive emissions, but you can harvest enough electrical energy to power your circuitry.
Wow. So you mentioned something interesting, that we now have the technology to do all of this. So do you think we're in the decade of science fiction becoming reality? I've heard that term thrown around.
Yes, and it always has in a way, but we live in the future, and again, we're lucky that we're inheriting a lot of the development. The optical laser was only realized in the early 1960s, and the fact that it got so cheap, that you can buy 10 small laser point. I mean, they're novelties. They're things that you annoy cats with now, right?
True.
They're giveaways, right? I mean, you go to the pet store and there's a cat, chaser laser spotter for $3, right? And I mean, it's amazing. But likewise, the cell phone technology, right? It's like the fact that there's a GPS receiver that has a antenna in it the size of your fingernail that can receive, 15 or more satellites at one time. And it's in a glass and metal box run by a battery that's running a cell phone and everything else. I mean, it's phenomenal. I mean, we're leveraging trillions of dollars of development and infrastructure to build these systems.
Yeah.
Super helpful.
Okay, let's see if we can get some more updates about the balloon launching. We really haven't heard anything, Andy. It's been quiet.
Do you so we'll ask you this. Do you think Mike or Josh also got stuck in a tree?
Yeah, I think in the past
I think they're most competent. I think they'll find it. It's a little bit of a needle in a haystack. I see Josh, so hopefully he's got it.
Yeah, we're trying to kind of piece together signals from the two different payloads. Hey, we initially looked at the route block data because that was still transmitting as of about 10 minutes ago, and we're getting some pretty frequent updates from it. But the route block position data has never, even on the website, it's not advertised to be particularly accurate.
Mm-hmm.
And we went nearby. We saw a couple white boxes in a field and got pretty excited. But it was quite a walk away, and then Mike decided to double check the last transmission he got from his payload. They didn't really seem to match up, so instead of walking for 20 minutes in the field, we decided to follow his signal first. And that's where we're at now. So we're still on the road.
So you just did like a little bit of a loop. I see.
Yeah, we can see your
path.
track.
Still looking at.
Are you centered in on one place that it will be, or what's the? Have you centered in on where it will be, or are you still just using visuals to find it?
Well, we're kind of guesstimating based on the last transmission, which wasn't too high. We're talking, I think, hundreds of meters. So it's not that windy out. It couldn't have moved too far from that last position. So we have a rough sense of where it should be, and we're honing in on that now.
Are you going by altitude too, like looking at topography?
Yeah, and we had the known altitude and the last known latitude and longitude, right? Relative to what our elevation is now on the ground. We can kind of just estimate how far could it have moved over that last few hundred feet or so.
Yeah.
Yeah. Okay.
Should we take a break?
No. Oh, I'll go get you some water.
Oh.
Yeah.
Okay.
We've been at this for a while. Sorry, guys.
Wait, can we take a momentary break?
Momentary break.
This has been interesting. I think we're gonna lose some.
Just look around for white boxes. Oh, that might be Sam's car. All right, I'm gonna tune out for a moment and get an update from these guys.
Apparently our sounds. Awesome.
Can we turn off the camera for a sec? Because we don't really have any updates.
Yeah.
And
So we'll go dark until we get updates. Hold on one sec. Audio. Let's see. Okay. We'll still be here to answer questions though, so definitely drop this in the chat. Let's see. Block has
we hold, I think, around 36 cube satellites at once.
audio. Let's see. Okay. We'll still be here to answer questions though, so definitely drop this in the chat. Let's see. Block has
We hold, I think, around 36 cube satellites at once.
Uh-oh.
Is your audio still on?
It's gonna loop again. I'm not sure how to turn the audio off temporarily. That is fascinating. I don't like this. hello, hello.
Hello, hello.
Oh, the upper part for sure. Hello.
Okay.
Hey.
He is not on yet. We're trying to figure this out. Okay.
How's it going, Josh?
I got a field. We're walking through it. Things are looking promising.
That looks like a muddy field to me.
Okay, how do we get this on?
Oh, the upper part for sure. Hello.
Okay.
Hey.
He is not on yet. We're trying to figure this out. Okay.
Why are we here?
How's it going, Josh?
Okay, so for all of you tuning in, we are walking through a field on the way to recovery. Yes, Sevi, we're back. As promised.
Hello,
Awesome.
everybody. We are back. So a little bit ago, we saw two white boxes in a field. Could have been some sort of farm instrument, and was about a 20-minute walk into the field. And wasn't really matching what we saw on our GPS data. So we passed it by and looked elsewhere, and we actually think that this coming back that these might be the balloon payloads. So we're really optimistic.
Approaching
and
the moment of truth here.
Approaching the moment of truth. Yeah. Josh? Can we see if we can see what you guys are looking at? Where are these white boxes?
There isn't much. They're dead ahead. I'm getting pretty close. But it's hard to see from my wide phone camera.
Maybe if you go landscape, we can see a bit more. Okay. Well, that's not quite it. That's
maybe switch back to profile.
Where it's just sideways at this point.
Landscape is straight up sideways.
So,
okay, so I'm seeing what looks like a building.
Did you have to contact this person?
So I reached the end of the muddy field.
Okay.
We don't know what the owners of this field are, and it's not like a backyard, right? It's a big piece of empty farmland.
Okay, well, be careful. Yikes.
I'm excited to see.
It's looking pretty promising.
So do you see any colors? Because wasn't the top payload also white, or is there any indication visually?
There's a couple white objects, some yellowish thing.
Okay.
Some red-looking things there too.
Any shimmering,
so it looks like. What do you say?
What color was the parachute?
I personally don't know. I think it was red and white. Oh, this is definitely it. Yeah. Okay. We should have.
Okay.
We lost an hour. We were here an hour ago. We should have made the walk.
Shoot. Okay. Well, here it is. Yeah.
Yeah, I recognize Martine's.
Wow. Do you guys have binoculars?
Little kind of circular.
Or? Oh, nice.
We some distance.
No, just an insanely observant person in a car.
Wow.
Here is the wreckage. And there is a somewhat deployed light sail.
Oh, hey.
Half sticking into the payload compartment.
Okay.
And it deployed, though.
And there's Mike's payload.
Awesome.
And then following this string is the parachute, which is yellow and dark red, maroon. And there's the broken pieces of balloon there too.
Wow. Wait, so Josh, what is a
Thanks, Mike.
What is a half deployed sail mean for us, for our visuals?
Probably not the best visual. And like again, I don't know at what point this happened, right?
Yeah.
It could have been that I received the command once it got to the ground and then tried to open, and that's why I got stuck.
Yeah, there is potential for that.
And I think that just has to do with the rock block connectivity that we're experiencing up there. It didn't start to get signal again, or we didn't start to get transmissions again until it reached near the ground. I'm on 1% battery, and it's dropping fast, so this might be the end from me.
Okay. Oh, no. Let's get one more
But I'm
shot
very
of the
glad to report
payload
that we
in.
found it.
Do you want to put Mike on?
You might
Okay.
drop that.
We're gonna have to talk to someone here. They spotted us in their field.
Okay.
Uh-oh. Okay.
Awesome. Well, congrats to the whole team.
Yeah, Mike's by his car, so it's quite a distance away.
Okay. Oh, we can still get him on.
Thanks.
Okay. Bye.
All right. Bye.
Do you have Mike's contact info?
No.
No. Okay. Well, we got it. So.
We got it. And
so the journey concludes here.
Yeah. Thanks so much for watching with us. It's been a full day of data and preparation come to fruition. And I'm sure we'll get some really awesome visuals, so we'll be sure to put that up for you guys. And
yeah, as Kent has said, we're gonna have some fantastic data, images, and videos to share with you in the coming hours, days, and weeks, honestly. And if we find that it didn't work, we'll do this again. Maybe not to this extent, but we'll certainly live stream it. So yeah, that's gonna happen, and hopefully we'll get some good stuff going.
Yeah, thanks so much for watching with us. And tune in next time if we're going for the second deploy. We'll be monitoring what our data looks like, what our video that we actually did capture look like, and we'll see if we need to do this again. Especially, let's see if the payload deployed far after apogee. So that's the one risk we have here. But other than that, yeah. Okay, thank you guys.
Yeah, so we'll I guess we'll post a full rundown of what happened somewhere, and we'll tell you where that somewhere is soon. We didn't really have this planned because we thought everything would work out. But yeah, check back. I guess this is very centralized, so check back at this YouTube channel for a breakdown of what happened. If not, just some cool videos.
Yeah.
Yeah.
Okay. All right. Goodbye.
See you guys. Have a good night, good afternoon, good morning, wherever you are. Take care.